to the Journey Shake Chem. Today I'm so excited. We have quite a warm-up to do first though, and it is in the further investigations of this lab. So please do the best you can and we will discuss it in a moment. Number one is a limiting reagent problem as well as some stoichiometry, and we had this in the first semester. And the very first thing that we must do is get a balanced equation. So we have methane and oxygen is being combusted, burning, and we get carbon dioxide and water for complete combustion. Now I'm given 16 grams of the methane and 16 grams of the oxygen, and I need to determine which one is going to be my limiting reagent. Well, 16 grams of the methane I need to change to moles. And 1 mole of methane has a mass of 16.0 grams of methane because carbon has a mass of 12 and each hydrogen is 1. When I solve this problem, I get 1 mole of the methane. Then I must change my 16 grams of oxygen to moles as well because I must have moles to make a comparison. I cannot compare grams. And there are 32 grams of oxygen for every 1 mole. And therefore, I have 0.5 moles of oxygen. Then I'm going to look at my coefficients. My recipe here calls for 1 methane for every 2 oxygens. And 1 is to 1 as 2 would be to 2. But I only have 0.5. 1 is to 1 as 2 is to x, and that x then would be 2. However, I only have 1/2 mole of oxygen, which makes it my limiting reagent. Therefore, that is what I'm going to use in order to determine how much of each component is going to be produced and what is going to be left over. It's very much like if I was cooking and I was making a cake and the cake called for 2 cups of flour and 3 eggs, but I only had 2 eggs. I would have to make the recipe only as much as could be made from those 2 eggs, the part that would run out. So here now we're going to use our 0.5 moles of our oxygen to determine what mass of the carbon dioxide. Well, I'm already at moles, and 1 mole of carbon dioxide is to 2 moles of oxygen. The coefficient here is 2 to 1. And then I change my moles of carbon dioxide back to grams, and there are 44.0 grams of carbon dioxide in 1 mole. And therefore here I get 11.0 grams of carbon dioxide. Then I also have 0.5 moles of the oxygen, and I want to know what mass of the water. And there are 2 moles of water for every 2 moles of oxygen. And 1 mole of water has a mass of 18.0 grams. And therefore I can do this in my head, half of 18 is 9.00 grams of water. Now I'm not going to have any of the oxygen left over. It's my limiting reagent, and I must address that in the lab because each one of these is worth 2 points. And so there is no oxygen remaining. However, there is going to be leftover methane. And I'm going to take my 0.5 moles, my 0.5 moles of oxygen, and I want to determine how much of the methane I'm going to need. Well, there is 1 mole of methane for every 2 moles of oxygen, and 1 mole of methane has a mass of 16.0 grams of methane. And this then gives me 4 grams of methane, and I originally had 16, so I'm going to subtract the 4, and I'm left with 12.0 grams of methane will be left over. And that's the 4th component of this reaction. And that's how you do number 1. Number 2 is one of the questions from the further investigations in the lab. Well, here we are given 0.50 grams of the copper 2 oxide, and we are given a 6 molar solution. And we want to know how many milliliters that will require. And I must change my grams of the copper 2 oxide, something new and different, to moles. And 1 mole of copper 2 oxide has a mass of 79.6 grams. Copper has a mass of 63.6, and oxygen is 16.0. And when we add them together, we get 79.6 grams per mole of the copper 2 oxide. Then I must switch compounds, and I'm looking for the sulfuric acid. And therefore, I have 1 mole of the sulfuric acid for every 1 mole of the copper 2 oxide. I didn't have a long enough line there. I had to add to that. I love doing that. Well, molarity means that we have 6 moles for every 1 liter. That's what 6 molar means. And this is, in essence, a conversion factor. And because I'm looking for volume, I'm going to put the 1 liter of sulfuric acid in my numerator, that would be the top of the fraction, and my 6 moles in the denominator, which is the bottom of the fraction. And then I change it to milliliters because the question is asking for milliliters. And there are 1,000 milliliters in 1 liter. Now, when I do the math here, I get 1.04690. And I look back to my original problem and I see I need 2 significant digits. Well, this 4 does not round the 0 up. And therefore, I have 1.0 milliliters of sulfuric acid. And we're going to do that today. I'm so excited. We're going to add the sulfuric acid to our cleaned up copper 2 oxide. And therefore, you remember, I left you at this point yesterday where we had the copper 2 oxide, and we're going into day 2 of the lab. We're going to decant off the water and clean up that black copper 2 oxide, and then we'll add the sulfuric acid. And it's so exciting. It's one of my favorite parts. So I can't wait to see you in the lab. Here we are in the lab. You know how excited I get? Well, yesterday we left our products sitting so that they could settle. And here is my beaker with my copper 2 oxide that is black. And it's been sitting overnight, and therefore the water is on the surface. However, there are also sodium and nitrate ions that remain from the prior reaction in this solution. And therefore, when I decant, some of those ions may remain on the copper 2 oxide, and therefore I am going to have to wash this precipitate. And to wash it, I'm going to need some hot water, and I always use distilled water in my reactions of anything that occurs with my materials. And therefore, I'm going to light this Bunsen burner, and here we go. Turn on the gas. Oh my, the main switch is off, and I will be right back. As you know, safety always comes first, and the main switch for the natural gas was turned off, and therefore I had to turn it back on. Now we should have gas, and I can smell it, and there we go, we have a lit Bunsen burner. And now we just need this water to be warm enough for me to see that very first bubble, and then it will be warm enough. In the meantime, I'm going to go ahead and decant the water from the solution very carefully, because copper could come out. Now, when the class is doing this, everybody has the same problem, and we try to gently, pour this off. That's sufficient. Because I'm going to be adding warm water to this, that is sufficient. Now, after we wash it with the warm water one more time, then we will add 15 milliliters of sulfuric acid, that is 6 molar. And you'll notice in this lab requires a lot of solutions of different concentrations. And this requires 6 molar sulfuric acid. And therefore, I have a graduated cylinder here that is the right size. And I'm going to fill it to 15 milliliters with this sulfuric acid. It actually has measurements on the side, but I'm going to go ahead and double check that we have 15 milliliters here. And it's also a double check for this container. And sure enough, that is 15 milliliters. On the button. So I had that ready to go of my sulfuric acid for this solution. But first, and I see there's already a bubble there in the beaker. Therefore, this water is plenty hot. I turn off the gas and I'm going to add, now the procedure calls for 200 milliliters. It's actually not critical the amount of the water. I just need to get a good rinse, and I'm going to pour in the hot water and stir to expose those sodium nitrates because they are soluble, and then I will let the solution sit. Again, we'll decant and then we'll be ready to add the sulfuric acid. And I'll be right back. While I'm waiting for my copper 2 oxide to settle, I am going to go ahead and weigh out the 2 grams of zinc that are required. Now I am going to zero my scale so that everything I put on here is going to be for the zinc. And it goes very, very quickly. One little 1/100th is all we need. And exactly 2.00 grams of zinc. And I will put that aside or bring that with me. Actually, we have to do this part under the hood. So I will put it under the hood and it will be there when we need it next. And I'll see you. I see that the copper 2 oxide solution is settling, and I'll see you right then. Here we are back with our solution. And I see that my solution now has settled pretty well. And students always ask me about the copper that could be in that solution that they could lose. Well, everybody has the same problem, and I've seen excellent results with this. Therefore, I'm going to go ahead and pour off as much of the water as I can without being too disruptive. And that should be fine. It's a little bit of water in there, but it's okay. Now I'm going to add my 15 milliliters of my acid, my sulfuric acid, and you're going to love this. Just have to be a little patient in order to see it, and I'm going to watch the solution very carefully. As I stir, 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 you can see it lightening up. Any minute. Woo! Look at that. That's just phenomenally most amazing. It went from solid black back to our beautiful blue copper ions in there. All right, now it's also very critical that all this black on the edges, that we get that into solution, because all of that is copper, and we want to make sure that we get it all off of there and into the solution. And the reaction is warm. This beaker is warm, and I think, let's see, there's some black here. I want to make sure I get everything off, because all of that is copper. In another form, copper 2 oxide, and now it's become copper 2 sulfate. Just going through all the changes here. Well, I think I got them all off. All right, isn't that beautiful? That's just beautiful. Makes you want to go swimming in the Bahamas. Okay, so now I will see you at the fan. Or I should say the hood. See you in the hood. Here we are at the hood. Now, we're going to pour in all of the zinc very quickly that I have already weighed out, 2.00 grams. And then I'm going to stir, stir, stir. This is a critical part for me to stir, because I must get the zinc in contact with the copper ions in the solution. And it's what makes the solution blue is the copper ions. And therefore, I must vigorously stir. I found that this is a critical part, because we must expose the zinc to the copper ions, because we want the solution to become clear. And we have to be very vigorously about this. The solution is clear on top of my copper, and my copper has returned. Isn't that nice? Now, we did initially see some bubbles in the solution besides what I was doing and when I was stirring them. And those bubbles show us that there is a gas that is being released inside of the solution. And in the warm-up question tomorrow, we will discuss what gas that is and how we know that it is that specific gas. Now I'm going to go ahead and decant this, and actually I think I'll leave it until tomorrow. And that's as far as we're going for today. Now, if there was a little bit of blue in the solution, that would mean that there were some copper ions that were left over. And that's why we had to stir vigorously, because we wanted to expose the copper ions in the solution with the zinc so it could be displaced. Well, that was some fun. I can't wait to see you tomorrow. Bye.